All right, thanks, Gavin, and welcome everybody, and thanks for joining Zebrium today, where we're going to talk a little bit about our new kind of log manager that detects problems and root cause automatically and autonomously. So just a couple of quick logistic points here. So we have a Q&A button on your Zoom session at the bottom there. You probably see that. If you do have any questions throughout the presentation, go ahead and type them in there. We're going to save those to the end, and then Gavin will walk through those, and there's a few of us on the phone here that are ready to answer all of that stuff, so we'll do it at the end. And also wanted to thank Gavin Cohen, who's joining me. He's our VP of Product at Zebrium. And after the presentation that I do, he's going to give you a couple of quick demos that highlight some of the great features in our product. All right, so let me get started with a kind of a little background on the problem that we set out to solve. So we all know in any system there's going to be problems. That's going to happen. There's no doubt about that. And we typically break that problem down into symptoms and then root causes, symptoms and cause. So when we're talking about sort of the DevOps world, or the SREs in that world, we're always trying to automate that process of trying to understand or detect causes and symptoms and remedy them. So in the case where the root cause and the symptom, you can set a trigger that says when this happens, then go do this. Maybe you automate a runbook process when that happens. So sort of best-in-class approach is really nearly total automation when you have sort of known knowns. The next case is, or next scenario is when maybe you know the cause or the symptom, but you don't know both. So you kind of tend to put partial automation in place, most likely, or you would want to if you could, whereby maybe you detect some variable. Let's say you're monitoring some metric and see some threshold getting too high or goes through a threshold. Maybe it's latency or some such thing, or user response. So it gets too high, you sort of trigger off an alert. The next thing that you're almost assuredly going to do is start hunting through logs. You're going to, gather up the logs and, from all your systems, and there could be millions of these that you're starting to dig through. But suffice it to say, there's some human intervention that's required for that last step to really try to get to the root cause and understand why that latency happened. Monitoring a metric's not going to really typically give you root cause ever. It's just going to let you know that that's a symptom, and then you're digging in. The last one is when you don't know anything about the cause or the symptoms that could happen. So with all the other ones, you sort of know something and you can set an alert. When you don't know anything about what might happen in that scenario, it could very well be that your customer is impacted, and they're the alerting mechanism. So they're the ones that are reaching out and telling you that something's gone wrong, or could be somebody internally, what have you. But in any event, you didn't have an alert set on that. And so now you're doing two things. You've impacted everybody potentially without any forewarning, and then you're digging in manually again. And so in that scenario, the entire process is all human intensive. It basically boils down to human search. So that's the problem statement sort of in a nutshell. What does that mean if we look back, let's say, to prior decades, so like the 2000s, look that far back? When an incident happened, it's probably a shrink-wrapped piece of software that was installed on-premise at your customer site. When that had an incident, it was going to impact that customer. Maybe it's some financial system, so it impacts the financial department of that customer. So maybe there's 10 users that are impacted. So it's not severe. It's not every one of your customers and every one of your users. It's very isolated. Today, however, let's say it's Stripe that goes down. Well, there's tens of thousands of customers with potentially millions of dollars of transactions at stake or in flight that are now stalled. That impact is significant and horrible in sort of today's modern applications. Back to that shrink wrap, from a complexity perspective, what would happen? So you have the problem, you'd probably go reproduce it in your lab, or maybe you got a bug filed on it, you sort of know what it is. You build a patch for them, you ship it out to that customer. It's not terribly complex typically to get to the root of that problem. It's fairly easy to reproduce probably in the lab, or however you might do that. But today, these systems are horribly complex, as probably a lot of you know, with maybe hundreds of microservices or more, running on potentially thousands of containers or hosts. That, when an incident happens there, now you're faced with that kind of an environment and that complexity and figuring out where is this problem, where is the root cause, how is it impacting what services, and it's probably being spread across many services that are getting impacted. So it just becomes very, very complex. So that's the picture today. But when we talk about the human getting involved to either see those or set up alerts or get to root cause, the human bandwidth has not changed over the last decade or more. We're still humans, and we're still struggling to try and get to the root cause of things through these manual processes. And so that's the problem in a nutshell here, is that human bandwidth has not kept up with what we've developed from a technology perspective when we're deploying modern apps today. And so what's the solution? So what are we doing about this, and how have we sort of looked at this problem? So everybody probably is aware of and probably uses various things like log management systems, maybe it's Elastic or what have you, and you've got metrics collection going on, and you're typically going to set alerts. You're going to build those alerts, custom alerts for those things. You see a particular log event or a particular threshold, again, metric going through some threshold. You're going to aggregate all of that together and sort of alarm yourself. So that's kind of the state of things. So there's some automation. Still, the speed to resolve things once you find it is that human interaction that has to take place. So next up was was the emergence of anomaly detection. So this is where you're seeing patterns change and you're spotting outliers, typically in metrics. Some systems are attempting to do that with logs, but again, mainly it's sort of metrics based. But the problem generally with this is there's still tuning that's required. So maybe you're tuning the models or trying to understand exactly what patterns are okay or not okay, and how do you detect these outliers within those new patterns and so on. So even with that, there's still a fair amount of human interaction that has to occur to either set it up or maintain it. Secondly, you often get a lot of false positives. So there's still a lot of noise in the system. So when you're looking at just a single anomaly in, let's say, a metric, that could be happening a lot through the day, and some of them might be quite normal. And so then you're back to the tuning aspect of it again. And then maybe some days that's not normal for that day. Maybe it's a seasonality thing or something so it's different. So in any event, you still have that problem when all you look at are single individual anomalies. It's still it's fraught with problems that helps to some degree, but these problems still weigh on the human factors as well. So what do we do? So we have introduced sort of another layer above all of this. So just imagine, let's say your anomaly detection is catching that 1 in a million event, that anomaly, 1 in a million. So today's complex systems, you might have millions of events or even billion events in a single day that are being logged from all of these different services or microservices and so on, and app level logs. So if you have a billion events and you're catching the 1 in 1,000, you're still got or 1 in a million, you're still got 1,000 things to deal with at the anomaly layer. So what we do is, and this is sort of the crux of the presentation that I'll go through, is how do you take those anomalies and distill them down to a meaningful set that represents an incident that has meaning and relevance and would likely root cause included in the description of that incident. So you don't need to go look at the 1,000 individual anomalies. And in this case, maybe you're looking at 1 or 2 or 3 things at most in a day, not 1,000 anomalies. So that's the solution that we are out to build to address that problem of human scale. All right, so I'm going to walk through just at a real high level, what our solution looks like, and then I'll dig in a little bit deeper throughout the presentation. So in a nutshell here, what do we do? So step one is we collect logs and metrics. So in a typical deployment of our collectors for let's say Kubernetes, it's literally 2 Helm commands. We now have your logs and metrics being sent to us on the back end. So very simple process, very, almost no human effort. In fact, when you look at when I walk through this slide, that's quite literally all the human effort that it takes to start identifying incidents with our system. Okay, in the middle is the real meat and potatoes of what we're doing, and that's taking those logs and essentially structuring them and doing some machine learning on them to identify those anomalies, and then understanding those anomalous patterns to pull together incidents that we then present back to the user. So that sort of structuring and machine learning, again, that's zero configuration. We don't have our customers defining how to parse the logs and what to look for and tuning different models or anything else. That's all autonomous. There's no human intervention for any of that. And then obviously with the incident detection follows on from that. And what we do there, when we identify an incident, we alert you. And so from 2 Helm commands to alerts, that's the process of the system that we've built. So what's sort of the underlying technology and how did we build this system? So how does it work? So there's 4 or 5 steps to the in the sort of the next layer down from that description that I just gave you. So the first thing is, how do we get those events that are coming streaming in from those log collectors into our system? And the objective there is to sort of categorize each one of those events into their own structure so that we can understand how each of those events are behaving. And so I'm going to walk through that part first, and then I'll come back to sort of the next 2 steps, anomaly detection and pattern recognition, where we create this virtual trace that leads to our incident that we present back to the user. Okay. So let me just first begin by restating that we ingest both logs and metrics. But what we started with first was logs. How do we ingest logs? And so why did we start with logs? Well, there's two main reasons. One, when you're trying to get to root cause, the answer is almost invariably going to be in those logs. And so that's a very important aspect to our objective of identifying incidents and providing the root cause for that incident. So we need logs. Second thing is, it's the hard part. Logs are very hard. Metrics are by definition almost fairly structured. There's a timestamp and there's a name to it and there's a value. And for the most part, metrics boil down to that. So they're fairly easy to ingest. There's not a lot of machine learning needed to go do that. There's a lot of machine learning to ingest logs properly. And so that's the hard part, and that's why we started there. So why, though, are logs so hard? Well, the first thing is changes to formats. So if you've ever looked at a log event, you can sort of generally, read what it says, and you can get an idea about what it's all about. But you're kind of at the mercy of the developer. The developer might change that log. And so let's say you were building a parser for that, and then the next release it changed. Well, your parser might not work anymore. So formats change. It's hard to deal with those changes automatically. And parses are ambiguous. So what do we mean by that? So let's say you take a log event and you're writing, you have one example of a log event. You say, okay, I want to parse this thing and sort of build a regex so that I can do something with it, like alert on it or measure some value in it over time or what have you. So you're building essentially a parser using a regex. So it's not hard to write a regex that will capture what you want. But that same regex, it's also not very hard for it to capture what you didn't want or didn't expect, just depending on how well you write that regex or what other samples you've seen. So it's often not the best approach to take a look at a single sample and expect that you're going to get a regular expression or a parser that will parse that thing perfectly and only that thing. And again, if something changes on you, even within that one, or maybe, maybe you just weren't parsing it perfectly, so you were getting either extra stuff sort of included with that regex, or if it changes, the format changes, you may not be getting what you want at all anymore. I mean, even if it was perfectly written and to only get what you needed, if that changed, you're not getting that at all. And now all of a sudden you're flying blind again. So that's very difficult to address. And changes and the ambiguity of regular expressions depending on how well they're built. And if you have seen or not seen every possible sample of your log events that are coming in, which unto itself is almost impossible. But the next thing is why logs are hard is that experts are often needed to interpret. So it's not always the case, but I know even in our own software, when I look at some of the log events that fly into our system, and we use our own system to monitor our own systems, that you look at something, and I've got to ask an engineer, what does PY mean in this where it says PY equal 43? Is that good or bad? And what does PY stand for, or whatever it is? So a lot of times you need somebody's help to understand those things. And therefore, if you were to write, going back to sort of doing some of this manually, you need to go ask and see, is PY important to monitor, or what does it mean, and so on, what does it interact with? So it gets, makes it difficult in that sense of having to go get some experts to help you out. And then finally, apps are bespoke by their own nature. I mean, you're writing your own app, or you're managing it, your own company's application, because that's what your company does. You build a product that's unique. And so it's not all off-the-shelf components. There's going to be some in there. You're going to have things like an Apache or an Nginx, web server and these sort of things, and there's plenty of parsers that are built for those. But there's probably 100 different parsers written for those kind of logs that you can go get off the shelf and then just work fine. But what about the thousands and thousands of events that your developers have put into the code that are essentially bespoke? There is no parsers off the shelf for those. You've got to go build them all. And again, to sort of understand that there are 1,000 or 2,000 of those and find them all and build proper things, it's near impossible. So that makes it, all of those things sort of contribute to why this is so hard. So what do we do? So step one of our machine learning is to structure those logs automatically. So what do we mean by that? So imagine you're writing that parser for a given log event. You can look at that and you can read that English text. It's mostly English. I mean, there's a lot of technical jargon in there probably, and other things you don't understand. But in any event, you can look at it and you probably get a pretty good idea that this thing is a timestamp and this is maybe a host name. And even for the event, so we call that part prefix, like where you're talking about timestamps and severity. That's the prefix of a log event. Sort of everything to the right is kind of the event text that the developer put in there. And that is, when you look at it as a human, you can sort of decipher what it is. Like let's say you see something, device disk 1 is almost full, or is 20% full. You know that disk 1, that name is probably a variable. Okay, you can, because it's the name of a disk. It's probably, you have multiple disks, it's going to be, vary over time. Different events will spit out the same message, but with different names for that disk and different percent fulls or percent error rates or whatever it is. You can sort of look at it and figure that out. Just because you're human and you've got some intelligence and you can just, you sort of know a bit about the system and everything else, so you can figure that out. But this isn't so easy for a machine to do. This isn't so easy for us to do, because we don't know everything about every application, but we have to learn that. That's what the machine learning is doing. And so how do we do that? So when we look at a log event as it's coming in, some parts are pretty easy to even assume are variable parts of an event. So for example, a number. When we see a number or integer or a float, we're going to assume off the bat that that's a variable part of the message. Okay. Other thing, and even IP addresses, we'll recognize IP addresses. We know how to do that, so we'll make those variable parts, or we'll assume they're variable. But what about other things like host names? Like, we don't necessarily know that that's variable. We just saw one example of something, and it says, I don't know, Hogan. Like, how do you know what Hogan is? I mean, you don't know if that's a host name or what it is. So So if you only see one example, it's very, very difficult to see the variable parts of anything except for those 2 or 3 things that I mentioned. And so what do we do there? So we basically, as we're seeing these things coming in, and this is all real time as we're ingesting the, right from those first 2 Helm commands that you do, we're going to take a look at every event as it's coming in, and we're going to make some assumptions about those things that are variable, and then we're not going to know other things are variable. But what we do in that case is, what we're attempting to do is take every unique event, okay, and structure it into its own table. So if you have 1,000 unique events that your developers put in and did printfs on for your bespoke app, and there's 1,000 unique ones, we will create 1,000 unique tables in a analytics database. And the columns of those tables will be all the variable parts. So for example, timestamp is variable. We know it's a timestamp. Everything else, that'll be a column. Severity, that's variable. We already know what those look like. That'll be a column. The numbers will be columns. The word Hogan, if we only saw one example, that was probably not going to be a column. That's going to get sort of put into the static part of the structure of that log. And that's not going to be very helpful. But it turns out that very early on as we're ingesting, literally within moments, whatever that is, minutes or an hour or something, we've probably seen a large percentage, over 99% of all of the events that are going to be seen have already been seen more than once. And so what happens there is we see another instance of that same event, and now we can, using machine learning, tell that it looks similar to something we've already seen, but it's slightly different here. And here it says Hogan, and there it says Dave. It's like, okay, that's a variable. Let's take all of those events now and structure it into a table where that part of the event is now a column in the database table. Okay, so now we're learning that as we go, and we're structuring these into tables. Now what happens, let's say, where we have done that and we've created that structure, but now the developer changes something, or maybe there's another part to that same event that happened to be the same in both of those 2 examples, so we didn't put it into its own column, but maybe a day later we see one of those. Well, what we will do is we will see that it's similar to that other table, but not quite, and we'll see exactly where it varies, and we'll create a new table for that one new event that came in with that now, let's say, 2 variable parts that we now recognize, and we will, through the next step of the pipeline, we will take those other 2 events that had Dave and Hogan in there, we'll actually merge those over into the table that we just created and make that other part also variable from those 2 events. So now we've got a brand new table with all the old data already moved over with the new column in there as well. So this is tantamount to you or somebody, maybe even, let's say, the engineer making a change to the structure of an event, even though it's the same event, maybe they've added a variable at the end or wherever. Your regular expression, if that's the thing you're parsing, will now probably no longer work, and it certainly won't pick up the new thing. There's no chance of that. We will have done all of that automatically, no touch. There's no rules that we're building to do this. This is what the machine learning does. It gets everything in the tables. So what does that mean? So there's no information required to actually understand the prefix. You don't have to define that for us. We figure all of that prefix information out ourselves, timestamps and severity and so on. We don't have to be told about specific log type keywords like this is an HTML access log, so look for these keywords, get and put and so on. We don't need any of that. Even the syntax or the grammar of that event, we don't need to be told any of that stuff like you would when you're writing a regular expression. This all just happens. And so we embrace free text logs. Bespoke apps just work with us. It's the beauty of it. You don't have to do anything at all for this all to work. So let me just take a relatively simple example of sort of the structure of an event here. So it's a fairly simple event, and I did this just so it's obvious where things get pulled out. But you see on the left is the prefix, on the right is the content of it. And you can see here that, I'll just point here, so you can see that this is the prefix. These all turn into columns like PID, timestamp, and we called that timestamp, and we typed it as a timestamp with time zone information, figured out the severity, and we captured that. And then for the parts that are variable, we actually determine which parts of these are variant. So this word here, this timing here, the number of milliseconds, those are all variable. So that becomes an int column. And these error counts, those are all variable. And so that becomes an integer column. So now we've structured this all automatically with no human intervention. So now we've got a great structured database of all your event types with all the columns representing whatever is variable within that. And so now what do we do with that? So it's the next part of machine learning. So once you have a complete dictionary of all these log events, what can we do with that? So we can learn the normal pattern of each event. So let's say there's those 1,000 tables. We can interrogate each of those tables and understand how frequently do these events occur, by event. What's the severity of those events, most often? What's the periodicity? So in other words, maybe they come out at 1 every hour for the first hour of the day, and then that happens, periodically, once a day. So we know that periodicity. So we understand these behaviors and the normal patterns of this. Now, the real trick here is, well, what happens when you break pattern? That's how we determine something as an anomaly. So in these examples here, so event 1. So we're moving along, and all of a sudden we see event 1 happen here. So we would declare that as a rare event. So that's an anomalous event to us, and it's anomalous because it's rare. So that one gets tagged that way. So under the hood, we've declared that event that occurred at that instant of time is now anomalous. Okay, this event 2. So a pattern change. So you can see it's frequency here that's occurring, and then all of a sudden, and even at the end here, it's back to that frequency. But right here, that pattern has changed. So we would recognize that. The beginning of that pattern change would become anomalous. So now we have a couple of anomalies, okay, that we've identified. Next thing is an event that's occurring at a regular pattern, and all of a sudden is no longer occurring. So it's stopped. That's another anomalous event for us. And then finally, it's all clean. This particular event type doesn't seem to be occurring at all, and then all of a sudden it starts. These might be particular error messages that are now starting because this maybe heartbeat message stopped occurring. So these are two very important signals for us, and they both become anomalies. Okay. So the next thing is, from what I'd said earlier, that's just not enough. Having anomalies occur, and these things might be occurring a lot during the day. You don't want to alert on every single one. So what we're attempting to do next is understand, for those, whatever there are, n number of anomalies, we're taking a look at a space in time to understand that the set of anomalies that are occurring there, is it rare or is it statistically improbable that that particular set should be occurring together now in this small time range? And if the answer to that is true, like this is just statistically improbable, it's like, okay, then something's probably wrong. So we'll sweep up those anomalies, and maybe that's 5 anomalies or 10 or 30. It's not going to be thousands, but maybe it's 20 or 30, let's say. It'll sweep that up into what we call here in this pattern recognition as a virtual trace. So each of these representing what you see here. So at this point in time, this one occurred, and then the next point in time, it was this one, and then this one, and then this one, and for these reasons, as you see here. So this is what we call a trace through time of that set of anomalies, and that becomes an incident. And that's what we're going to present to you. And it's almost true every time, and you'll see it in the demo, and then that demo is not rigged or anything. But typically, when something does go wrong, the things that are anomalous early on in that trace are going to be probably presenting as root cause. So that's where you would look. So this one might be the worst of the worst of them because of severity or amount that's happening or whatever the reason is. But let's say that's the worst of the worst within this incident. But this one is very likely having something to do with the probable root cause of why this rest of this trace happened. Okay. So that's how it works. And, oops, sorry. So the bottom line is we trace these unknowns. So there's no information included or required about like connectors, like, how do you parse an Nginx log or anything like that. We don't need any knowledge bases. There's none of that. We don't have to understand any specific application behaviors, like when there's a 500 error, then this happens, or blah, blah, blah. None of that is required. No semantic keywords on how to parse anything. That's all figured out autonomously with no human intervention, no touch. And of course, it works great on bespoke apps. I mean, that's the whole point. Okay. So with that, that's the bottom line of what we're doing, why we're doing it. And I think now I'm going to hand it over to Gavin, who's going to do a couple of quick demos and sort of show you a bit about the product and how it works, and show you some of these incidents and how they get detected and what they look like in our UI. Okay, Gavin, thanks.
Hey, thanks, Rod. So appreciate that. And what I'll do now is I'll demonstrate what this looks like in real life. So what you're seeing now is the overview screen that you would see as soon as you log into the Zebrium service. And underneath that, you can see some pretty interesting information. Now, this instance of Zebrium has logs from our internal Atlassian instance where we run Jira, Bitbucket, and Confluence. So over here, you can see there's some information about what we've collected. We chart out over time the errors and anomalies. And then you heard a lot from Rod about event types. So what we're showing you here are the top event types by severity, error, and warning, and then the top anomalous event types. But what's really interesting and important here is that underneath all of this, and yes, there are always these noisy anomalies, we've detected one single incident. And that's really what our machine learning is good at picking up. These are these virtual traces that Rod referred to. So let me click on that, and you're presented with a single line summary where you can see there's some kind of an unhandled exception, which sounds ominous in Jira. So now I'll click on that to get a summary of an incident, or what we call an incident report. Now, the first thing you'll notice is this incident spans Confluence, Jira, and syslog, okay? And here's that single line summary message, which we call the hallmark event. But right at the top, you get a sense actually of exactly what happens. And it turns out this is a very descriptive incident. Now, just to be really, really clear, there was zero instrumentation or knowledge that our system had about the Atlassian environment. It picked this up because of this cascading anomalous set of log events that occurred across these logs. And it starts with this one. Now, what's of note here is this is a message from syslog, but it's not an error. So there's no error severity. In fact, it's an info level message, which again, wasn't instrumented in any way. And it says stop Postgres. So pretty clearly, if Postgres is stopped, there's probably going to be some sort of impact to the rest of the Atlassian apps. And sure enough, if you look a little bit further down, you can see over here, there's a connection issue from Jira, and then a failed query again from Jira, then the one that we saw earlier. And then a little bit further down and a few seconds later, you can see how it cascades. This time there's an event from Confluence. Now Confluence, it turns out in the Atlassian architecture, doesn't talk directly to Postgres, but it does talk to Jira. So it hit an error while it was trying to get Jira metadata. So this is all perfectly in line. Postgres stopped, and then the rest of the app started falling over. Now, this was picked up because our machine learning saw this sort of set of anomalous patterns across the logs. It turns out, just so you know, what really happened is one of our guys had logged in and shut down Postgres without telling the system, of course, and this is what we picked up. So pretty clear cut. Now, I don't have to because we kind of know what happened here, but if I click view all events in the log viewer, I can drill down further and do further troubleshooting if that were necessary. So what I'm presented with over here is a filtered list of those same events that make up the incident. This time they're displayed very much like they would if you were to look at the raw log stream. So you can see the syslog, the Jira, the Confluence events. We can expand the metadata and see what else our collectors picked up. But there are a few really nice shortcuts that we can do if you're in the process of troubleshooting. And the first one is our peek function. So if I click over here on the right-hand side, peak, what happens is I'm taken into this exact log stream where the stop Postgres message came from. And this comes from syslog, as we saw earlier. Now I can see what happened before and after, and that sometimes yields more information about the problem. And this is great if you're in a microservice environment where you have thousands of identical syslogs from each instance or each pod or each microservice. You're taken to the exact stream where this event occurred without having to go hunt for it. So that's what peak does. The other thing we can do is get much more of an overview of everything. So remember I said we came in with a filtered list. So over here you can see there's a filter that's turned on. If I turn off the filter, then I get to see our aggregated view around what happened. So this time we're showing you all the logs that were collected, starting with here's our Postgres stopped message, and then before and after you can see what goes on, and you can see there were a fair number of events that occurred between some of the anomalies that we picked up as part of the incident. So like I said, this is pretty clear cut. I just wanted to show it to you as an example of how we pick something up autonomously. I'll just point out a couple more things. At this point, we're also a full-blown log manager. So we support full regex compliant search up here. You can filter by log type, you can filter by severity, you can filter by any of the labels that we pick up. And again, we'll pick up all the Kubernetes or the labels that we get from CloudWatch or wherever we're collecting logs from. You can filter by regex searches. We can set up these maps, which give you a chart over time with intensity showing the number of events for particular things that you set up, and we can set up custom alerts as well. So all the usual things. But I'll just point out a last thing on this example. Rod talked a lot about how our machine learning structures the events without you having to tell it anything. And here's a great example. So this is our info level stopped Postgres message that you saw. And what you can see here is there are some words in blue, and then there's this word PostgreSQL in white. The words in blue are what we've picked up as variables within the event, meaning there are other events that are like this, where likely there are different values in that place in the log line in the event. And so what I can do, because we've put these things into columns, I can click on the word stopped, and I can say display chart. And what that does is it shows me over here, and you can see stopped Postgres at 4:17, and then over here at 4:19, we can see starting and then started. And that's exactly what happened. Someone had logged in, they stopped Postgres, 2 minutes later, they started again. So this was pulled out entirely by our machine learning, and we can chart it because it's a variable in one of our tables for this event type. So that's the first example. What I'll do now is I'll show you kind of an interesting use case, which is our second example. So really, you saw this notion of we detected something autonomously, and then we showed you the incident report, which gave you the root cause. A lot of people ask us, well, I already have some sort of a tool. I have an APM tool or a monitoring tool or some other logging tool. Can I still use Zebrium? And the answer is, of course you can. You can always, and how we are more often than not used is we become, especially over time, a replacement for whatever you have. But if you want to keep what you have, that's just fine, because we offer something pretty cool, and it's called an augmentation mode. And this is where we can take incidents that come in from a third-party tool, could even be your help desk, and we augment it with further detail, with root cause. So this is to help you with the troubleshooting process. Of course, because we're in the loop, we can also use our machine learning to catch this whole long tail of problems that you didn't instrument for. So these kind of unknown unknowns are the ones that it was just too difficult to build alert rules for. We can catch those and help you. So in this second demo, I'm going to show you what that looks like in real life. And it's really pretty cool. And for this, we're actually using our PagerDuty integration because it pulls everything together really well. So where I'm going to start now is inside Slack. And this is the channel that's been set up to receive PagerDuty alerts. Now, we had a real incident in our Atlassian, actually our production Atlassian environment that happened in the past. For the purpose of this demo, I'm going to ask Rod now in the background to trigger this incident as though it just happened, so you can kind of see in real time what it would look like. So Rod, if you can hit your...
Hey, Gab, I'm not sure I'm seeing your Slack channel. Should I be?
You should. That's a really good... Let me just make sure that I'm sharing everything, which I thought I was. Okay. Okay. Thank you. Thanks for pointing that out, Rod. So if you can trigger the...
I'm going to go ahead.
Thank you. Okay. So Rod's just triggered it. And there you saw kind of two things happen. First, we got the PagerDuty notification saying that it's had an incident triggered by the APM tool because there's a critical health rule violation, and we get to do whatever we want with it. And I'll show you, we'll drill down further in a moment. And then very soon after, you saw Zebrium's augmentation. Now this is pretty cool. Three things actually happen when PagerDuty gets this alert from the APM tool. The first thing is PagerDuty sends a signal to Zebrium to request augmentation, and we respond back with any incidents that match the context that we detected. So these are the autonomous incidents that we detected within the previous half an hour. And that's what you see here, okay? So this is kind of our view, and you'll see in a moment when we drill down, of what was actually instrumented in the APM tool. The second thing that happens is we continue to monitor for the next half an hour and talk back to PagerDuty, and any further incidents that occur will also appear in the same PagerDuty incident. And that's pretty cool, because if you're troubleshooting and things start going haywire or that are all related, you'll see them all automatically populated inside your PagerDuty incident. And the third thing we do is we generate what we call a synthetic incident. And this is essentially because we've had a positive signal to say there is a real incident, we collect together all the anomalies and other info that are useful for someone troubleshooting that occurred within this same time period, and we put it into a synthetic incident so that if you're troubleshooting and you need sort of more detail beyond what we pick up in our machine learning generated autonomous incident, you get that as well. So it's all pretty cool. Now, let's go and sort of explore a bit further. And for that, I'm going to click here and go into PagerDuty. So now we're actually inside PagerDuty, and we can see the incident that Rod had triggered. So this is actually now the real incident that you're seeing. And essentially, it's this health rule violation. It's critical. It was triggered because presumably a login time here, it exceeded 60 seconds. We can look at the incident timeline. So it was triggered. And then here's our Zebrium augmentation. So let's go and see what Zebrium sees. So I click here, and now I'm taken into Zebrium, and we get put directly into that incident that Zebrium had generated at the time that you saw the APM tool. So this is pretty cool what happened. So PagerDuty got the incident because the APM tool was instrumented because of this 60-second threshold. But let's start with Zebrium, with the hallmark event, and we see, again, a pretty nasty looking, it's another unhandled exception, and there's a 60 seconds timeout here, or recovery, which sort of aligns with the 60-second login timeout. So presumably it's the same one. But like before, let's scroll up and look for the root cause. Now, this is actually very cool. So again, nothing was instrumented here at all from our side. This was just collecting the logs and metrics. The very first event that you see in this incident comes from the kernel logs. And essentially it says the kernel invoked the OOM killer, okay, out of memory killer, because it was running out of memory. And what did it kill? Well, it killed a process called OOM test. Guess what OOM test is? It's an app that Rod, our friend over here, had actually run, and its sole purpose is to consume as much memory as possible, and it was running on the same host as Confluence. So it essentially sucked all the memory away from Confluence, and what actually happens is it sucked all the memory, and then Confluence starts to fail, and you can see there's a bunch of bad things that happened beyond that because it ran out of memory. But fortunately, the kernel picked up this rogue process and it killed it. So let's have a look. In this case, we have Prometheus metrics as well as the log events. And you can see here, this one's very much in line with that, where there's no, you can see the free space plummeting, swap space plummeting, and then, the OOM killer kind of gets invoked. So once again, straight to root cause. I could drill down into the metrics and see what was going on. In the interest of time, I won't do that, but I will show you one other cool thing. So this is the incident list for this environment. Actually, there's a second really cool one that we generated. And it turns out, again, without instrumentation, that guess what? We picked up also when things came back to life. So you can see, recovery job successful. This comes again from Confluence, which was the thing that was affected before. And essentially, as our memory, we had enough memory to start running again, Confluence kicked off its job again, and everything was healthy. So this was also autonomously picked up. So I know I've stated this a few times, but no instrumentation. We didn't teach it anything. These two were picked up entirely because this OOM test was run, and that was it. It was picked up. Yet for the APM tool, they actually had to instrument an alert to pick up something without details of what actually happened, what the root cause was. So let me just wrap up with a couple of slides, and this will sort of tie it all together. We can show you what you just saw. So PagerDuty here, the incident was triggered by the APM tool. PagerDuty created an incident. It requested Zebrium to augment. Zebrium augmented, and it added in its incident and root cause, which you saw right inside the PagerDuty incident. Okay. Now, it's pretty cool, the kinds of things that we pick up. And I'm just going to give you 3 quick customer examples. And we have many more, and you can look at our website and you'll see some more, and we can certainly discuss any with you if anyone's interested. Reserved AI is a vendor that provides a very cost-effective way of buying AWS on-demand instances. And they obviously leverage the AWS APIs very heavily. And it turned out that there was a change that Amazon implemented that essentially broke their service. Now, Zebrium detected it as soon as it first occurred. But what was really cool, not just that it detected it, because it actually did severely impact their service, so they would have noticed it at some point anyway. It was that we detected it in a way where they immediately saw what the problem was. They didn't have to go hunting for root cause. Logics, a fintech company, had for a long time been seeing these really odd error messages that were troubling them. And they had tried again and again and spent literally days on this, trying to uncover what was going on because it didn't match what their code was actually doing. Anyway, they installed Zebrium, and this happened very, very early on. We detected an incident, and sure enough, those same odd error messages appeared. But this time they were correlated with other events that they didn't realize, and that pointed straight at the root cause. And it turned out there was a pretty important bug in their code. We found it, or we gave them enough context to find it very rapidly. They fixed it, and they now have closed something that could have been a potential big issue for them. Maya Data, you might know them. They're responsible for writing and maintaining the CNCF project for OpenEBS, and they also built a chaos engineering tool for Kubernetes called Litmus, which they run. They have a production OpenEBS service, and they wanted to sort of put Zebrium through its paces. So they actually ran some chaos engineering experiments on their production OpenEBS environment. They ran about a dozen experiments, and Zebrium created a dozen, I think it was actually 13 incidents, and we pretty much nailed every single one of the experiments in terms of picking up what happened, root cause, and some of them actually turned out to be some things that they didn't even know about in their code that really helped them. So I say that because it kind of demonstrates the breadth of what we can do. And in that vein, you can see this slide again covers really the breadth of the types of incidents that we pick up. Now, this is not meant to be an exhaustive list. It's just meant to show you the variety of things that our machine learning picks up without any kind of instrumentation. So that's the end of the formal presentation. I noticed we've had quite a few questions coming through, and we're sort of heading towards the end of time. So what we'll do is we'll address them now. What I'll say just as well before we wrap up, please try the tool. It's completely free to try, and there is a free tier that you can use forever. It's a pretty generous free tier. Just visit our website and click the sign up link, or here's the URL directly. We're a small company, so we're just, if nothing else, we'd love your feedback, but it's dead easy to get started. It takes about 2 minutes to set up and install our log collectors, and that's it. You don't have to do anything beyond that. So I'm gonna flip over into the Q&A mode, and there've been a couple of questions. So let me start with the first one. And the first one says, how does Zebrium compare to other log managers like Splunk or Elastic? And I'll just quickly take that. Essentially, like Splunk and Elastic, we all, including Zebrium, we do the usual aggregation and search and all the functionality you'd expect inside a log manager. But the challenge with log managers is really pretty fundamental. Number one is, if you want to be alerted, you need to set up alerts. So you have to know what to build rules for. And number two is, when you're troubleshooting, you have to know what to search for. Now, what's the difference with Zebrium? Well, that's what our machine learning does. So you saw pretty clearly in the examples, not only did we pick up these incidents without instrumentation, but we saved all that troubleshooting and hunting, all those steps to get to root cause. So that's really where we're different, is in this notion. And it's not machine learning that's been layered in later to try and do some anomaly detection. This is the notion of machine learning for real incident detection. So that's that question. There's another one which I might let Rod take. It says, does your anomaly detection work with custom apps? So Rod, do you want to cover that?
Yeah, thanks, Kev. Yep, of course, and I think I covered that in some length, a little bit at least, in the presentation. So yeah, I mean, that is what essentially our claim to fame. I mean, you don't have to instrument anything or write parsing rules for any kind of log. So for bespoke apps, we're absolutely perfect for that. Even though this was Confluence and Bitbucket and everything else that we showed, to us that was sort of a bespoke app, and we didn't have any prior knowledge of what kind of events or anything else that those tools are going to spit out. So yes, indeed, it's very, very suitable, and literally probably the only thing on the market that can do this level of anomaly and incident detection and root cause automation all autonomously. So hopefully you get a chance to give it a shot with your app.
Okay, thank you, Rod. And then a couple more, just I'm a bit concerned we're going to run out of time, but please do keep them coming. And if anybody wants to ask questions and we don't get to them, we will cover those offline. We'll email you back with it. So just please keep asking questions. There's a quick one that says, how much does it cost? Basically, go and have a look at our website. There is a pricing page. It's pretty straightforward and transparent pricing. We charge on how much data you send us, and it's very cost effective, especially if you compare us to some of the services offered by our competitors. And we also, there's a charge per metric host, which is a fairly nominal charge, but have a look at our website and you'll see. And then the augmentation mode as well is priced at a lower rate, because you're not really leveraging us as much as a log manager. You're leveraging us really for our machine learning. So again, have a look on the website. And the final question that I'll take here is, if I have an existing logging solution, do I need to replace it? So I covered this really in my demo, and the answer is yes or no. I mean, obviously, over time, I think you'd find we're a great replacement because we're really doing what the log managers do or what the monitoring tools do, but we're also offering this whole machine learning incident detection and root cause augmentation or root cause enrichment that you saw. But if you don't want to, you can run us in the augmentation mode that I demoed when I showed you with PagerDuty. If you don't have PagerDuty, you can just use Slack as the central place to do all of the incident management. And in that mode, we're both more cost effective, but we also will then augment what other tools can already provide. So when really cover the stuff that we do well. And I believe, Rod, were there any other questions there?
Yeah, so I just saw one come in. So do we need Zebrium agents to be installed on our servers or containers? So we have several, we support several different environments. So we do have our own agents available that for Kubernetes, for example, and as we said, that's a simple Helm install. And then we have agents for Docker environments and as well as in Amazon with Docker and EPS. We have Linux collectors. One thing we are looking at is, we also have syslog forwarders. So if you have a existing remote syslog infrastructure, that all works as well. So generally, yes, you would have to install our collectors. We are doing work to sort of simplify some of that to coexist in other ways with potentially things like Logstash, for example, where that would make that much simpler. We already do that for some environments and some different feeds coming out of Logstash where you can just put an output plugin for us. So anyway, that's always getting extended as we see more and more need from different environments. Hope that answers that.
Cool. Thanks, Rod. Well, look, we're at the top of the hour, so I just wanted to thank everyone for joining. We're absolutely available. You can see both mine and Rod's contact details on this slide, or ping us via the website or online chat. We're here to help, and we'd love you guys to try it. And so thank you, everyone, for attending. If we didn't get to your questions, we will email you back post this webinar. Thank you, and really appreciate you joining.